Okay, so here we have a spring problem, and this problem says that the spring starts out with an unstretched length of 1 meter. And it says if you hang a 5 kilogram mass from it, it will stretch to 1.1 meters. So they want us to find the spring constant. And then they say if you pull it 2 centimeters away from its new equilibrium position, so the new equilibrium's at, if we draw a picture, this is the unstretched spring, 1 meter. And here's the stretched spring with a new equilibrium of 1.1 meters. Okay, they want to know find the period and the amplitude of the resulting oscillation. So, first things first, they want to find the spring constant. Okay, well, if you recall, for a spring, the force that a spring exerts when you pull on it is K times delta x. In other words, if you pull it some distance delta x, it will feel a force that is k times delta x. Well, they tell us that when we hang a mass from it, it goes from 1 to 1.1. So at the very least, we know delta x equals 1, let's say this, 1.1 minus 1, right? Because final, initial. So this is 0.1 meters. Okay, so I can put on this side k times 0.1. The problem is I don't know k and I don't know the force. Or do I? What we're saying is that I'm putting something that has weight on the spring. So it's actually the weight of the thing that is pulling on the spring, and the spring is pulling back up, and these two forces are balanced. If you remember from the mechanics unit, the force of weight is mg, where g is 9.8 meters per second. You can use 10 too if you want, but this is m times, I'll just say 10 meters per second squared. Okay, so that means that the force that this is actually equal to is the weight. So that tells us that mg, let me plug in, I have 5 kilograms for the mass. For g, I'm going to use 10. That equals k times 0.1. Okay, and this gives us a k of 50 divided by 0.1, or 500 newtons per meter are the units for a spring. And spring constants tend to be pretty big. 500 is a perfectly reasonable number to get for a spring constant. So that's the spring constant. A nifty formula, if I hadn't plugged in any of these numbers, if I had just said mg equals k delta x, this is a good thing to hang on to. If you want, you can rearrange it to say that k equals mg over delta x, although there's no guarantee that the problem is going to ask for k. Maybe the problem will give you k and ask for delta x, in which case you're just going to have to rearrange it again. So if you were to remember something, I would tell you to remember this. For part B, okay, so it's at its new equilibrium position. It's here and it's very happy, right? The spring force is balanced by the weight, okay? But if I tug it down 2 centimeters, so 0.02, right, then the spring is going to pull up harder than the weight is pulling down. So it's going to pull it back toward equilibrium again. It's going to pull it up here, back toward equilibrium, okay? Once it gets back to equilibrium, the spring force will again equal the weight, but by the time it gets to equilibrium, it'll actually have some speed, so it'll be moving upward. And if it's moving upward, it'll overshoot the equilibrium position, and then the spring will be less stretched than it was, and now the weight is going to be greater than the spring force, so the spring is going to start falling back down again. And when it falls all the way back down to equilibrium, again, the spring force will be equal to the weight, but the thing will be moving, so it'll shoot past that point. And so the resulting motion will definitely be oscillation. Okay, it'll be oscillation. So it'll look something like this. Okay, so this is the original equilibrium position. You know, this height might correspond to this line that we have here, this equilibrium position, okay? And this is the maximum it gets away from equilibrium. So that's actually the amplitude, right? And this, the time it takes to go from one highest point to the highest point again, that's what we mean when we say the period. Okay, so the amplitude, believe it or not, this we can just pull right out of the problem. If you tug it 2 centimeters away from its new equilibrium position, its amplitude will be 2 centimeters. A really easy way to see that that's true is if you have a spring and you tug on it and you're holding it and it's displaced from equilibrium, then it's got a little bit of extra potential energy. It's got an extra 1/2 k times delta x squared's worth of potential energy, and it has no kinetic energy, so ke equals 0 because it's not moving, right? And so the question is, if it starts that far away, this is where it starts at A, how far will it go to the other side? It actually has to go the exact same distance, because when it gets to this point, it also has no kinetic energy, because when it's at the peaks, it's at rest. And if it has no kinetic energy, then it has to have the exact same extra elastic potential energy that it had the first time. And so this number has to be the same. In other words, we pull it out 0.02, and it'll go to 0.02 on either side over and over and over again because of conservation of energy. Okay, so the amplitude's easy. A equals 0.02, okay? Meanwhile, the period, and we won't derive this in this class, although one could derive it, but we're not going to. This is 2 pi times the square root of m over k. And you notice, if you look at this, it doesn't matter how big the amplitude is. The amplitude has no effect on the period whatsoever, okay? So here, this is just a matter of plug and chug. We can say 2 pi times the square root. The mass is 5 kilograms, and the spring constant is 500, okay? So this is 2 pi times the square root of 1 over 100, which is 2 pi over 10, and we'll plunk seconds on at the end just to keep ourselves honest. So that is the period. Okay, hopefully this was helpful. There's plenty more to talk about, but I feel like this is a good start. If you have questions, feel free to ask.